All right, hello everyone. So today we're going to finish up our unit on design patterns. This is the last new unit, or the unit of new material in the course. So what we cover today will be on the exam. However, so next Tuesday, exam review, I will put up a study guide tomorrow. We will then have just open questions about material. So I will not come with prepared material. You should come with questions ready. I will go through topics one at a time. From there, pardon me, homework 7, of course, is officially due April 28th, but it will not be marked late. If you submit by Saturday, May 2nd, that is to say, that will be on time. Sunday, May 3, that will be 5 days late. So just be aware of that. And again, you can, both my kitties are kind of wound up right now. You can see Colby in the back there. Again, you can submit. So the exam is the official exam day for us, which I believe is May 5th. Hang on one second. UVA, final exam schedule. I believe it's May 5th. It's whatever the official day is. So I can't override the school there on that end. So the exam, yeah, if you take a look, it is Tuesday, May 5th. It says 2 to 5 p.m., so this will be an online exam. It will be open from noon until midnight. That 12-hour window should be more than enough. As a reminder, with the online exam, if you start, so hypothetically, let's say the exam is a 2-hour exam. And if it's a 3-hour exam, I'll probably give more than 12 hours to take it. But let's hypothetically say for now it's a 2-hour exam. If it, and I haven't written it yet, so I don't know how long it is yet. But if it were a 2-hour exam and the cutoff were midnight, if you started at 10:30, you would not get the full 2 hours. You would only get an hour and a half. So all those details will be finalized by Tuesday, and I'll discuss them then. But it will be Tuesday, May 5th, and it will, of course, be online. It'll be on Colab. Structurally, it will be similar to what we did on Exam 2. And my cats are just going absolutely bonkers right now. Sorry. But that's when the exam is. Any other questions? And again, this content will be on the exam. So the exam will be biased towards material covered since Exam 2. That is to say that more of the material will be from after Exam 2, like the Exam 2 to Exam 3 period, then will be Exam 1 to Exam 2, or from beginning of class to Exam 1. That said, the exam is cumulative. So do be aware of that. Any other questions? Any other questions? Okay, one other thing, and this is kind of just an off-the-cuff announcement, but the student evaluation should open, I believe, the 27th, which is next Monday. I will make the following arrangement, assuming that I can still see, because the student evaluations should still be on Colab, and I should still be able to see who has done it. Here is the rule. If you do the evaluation by next Friday at 11:59 p.m., and I just got an email this morning explaining that it should be out the 27th. If it's out later than that, certainly I can adjust this policy. But currently it says it will open the 27th. If you complete your evaluation by next Friday, which is May 1. Oh, this is falling off the screen, isn't it? Hang on, I can fix this. Then, and again, I can see who has taken it, but of course the feedback itself I won't see. I will only see who has taken it. Then I will round your grade up to the next percent. I want to be clear what I mean by that. Yes, that would mean, for example, if you had an 89.7, that would become a 90, but that would also be true if you had an 89.1. That would round up to a 90 as well. So this is just an incentive to provide feedback. I want to be clear, I do want the feedback to be honest. I will not see who gave what feedback, but I will be able to see who has responded. So, if you do the evaluation by next Friday, and this deadline won't be extended, specifically by next Friday, May 1, then I will round your grade up. Now, there's no easy way for me to show that in Colab, but it will be done. Do you eventually get I will eventually get to see the feedback, but it is still anonymous. I want to be clear. So I don't know who provided specifically what feedback. All I know is who provided any feedback. And then I see the feedback later, but I can't connect it to any individual person. So it is anonymous. And I do see the feedback, certainly, and I do apply the feedback. That's why I want the student evaluations done. And of course, this semester's incredibly weird, so certainly it makes it difficult to evaluate courses, I know. But please do the student evaluation by next Friday. If you email me Saturday morning saying, oh, I forgot to do it, I'm going to say, I gave plenty of notice on this. I'll remind everyone next Tuesday. Do the student evaluation. I'll even put up a Piazza announcement for this after class. All right, so today we're going to talk about 4 design patterns. We're going to talk about the bridge, the decorator, the observer, and the adapter. So let's just go ahead and jump into it. Structural design patterns, that should not be strategy pattern. That should be decorator. Structural design patterns are patterns for how we combine different objects that necessarily might need to work together. Oh, sorry, I don't have screen share on. Now, we're going to start with the bridge pattern, and the bridge pattern is described by this sentence. Decouple an abstraction from its implementation so that the two can vary independently. And this sentence is actually quite amazing because when I first read it, understood every single word individually. I know what decouple means. I know what abstraction. I know what implementation. I know what it means to vary independently. But when I read this sentence, I think that. It's kind of an intense sentence. So what does that actually mean? Well, the bridge design pattern, we'll get to what this sentence means. So, what we want to do is maintain a separate inheritance hierarchy that allow a client to assemble combinations of items. Here's an example of this. And we'll get to the idea here. We actually will implement this. The example of this is that I have some client trying to draw some shape. And the shape could either be a square or a circle or a rectangle or any number of shapes. Additionally, we have the color renderer and the grayscale renderer. Now, the idea of this renderer is that each shape can be drawn, and how it's drawn can be customized independent from the shape. That is to say, rather than create something like 4 different classes: color circle, gray scale circle, color rectangle, and grayscale rectangle, rather than do this, because keep in mind, if I add a single shape, I have to add 2 classes, one for each renderer. And if I add a renderer, I have to add as many classes as I have shapes. So this could blow up in complexity. Rather, I can separate these out where each thing is one class. So the number of classes is the sum of the number of shapes and the number of renderers, rather than the product of the two. So the more shapes I have, the more renderers I have, the more this will benefit. And the idea of the bridge design pattern is I have some abstract idea, like a shape, and that shape has some feature that I can implement as a separate hierarchy. So in this case, the shape feature that I'm separating out is drawing a shape. I'm putting that into a separate hierarchy where the abstract hierarchy has renderer as the primary abstract class. So this is in charge of drawing shapes, but I've separated out from the shape itself. And so we want to be able to do something like, and this font is not showing up particularly well. Let me, well, that's not helping. Let me do this. One sec. There we go. Let's say I have some list of shapes. I would then want to be able to create, say, a grayscale circle like this, and a color rectangle like this. And this will allow me to create the shapes and then iterate through and just simply call draw, and the draw function will call the relevant function in these classes. So this is similar to what we did with the design patterns. So let's take a look at how this is done in code. Pardon me. So if we take a look at the bridge design pattern, the first idea is I have this shape class. And it's an abstract class which has a renderer. This is the thing that performs the feature. Remember, I'm taking a feature, I'm exporting it to a separate hierarchy. And so this, whoops, hang on, I accidentally deleted something here. So this renderer is owned by the parent class, by the shape. So that's the shape has a renderer relationship. From there, I have 2 classes that extend shape, that is to say they realize shape, rectangle and circle. You can see here that effectively these are just passed through. But the key is these classes, their constructors also take in a renderer object. That is, they take in some kind of renderer that gets stored in the parent class. And so our parent class constructor takes in that renderer, stores it in my renderer, and the child classes simply take this renderer R and pass it to the parent constructor here, similar to how we've seen in inheritance before. From there, I define my draw function simply by saying whenever I draw a circle, I'm going to use the renderer object that I passed in at construction time. I'm going to use that renderer object to draw the circle. That is to say, I won't implement draw inside of the class circle. Rather, I will implement draw inside of this renderer. And similar to draw rectangle inside of this renderer. So you can see, at least so far, we have covered the left side of this hierarchy. That is, a client interacts with shape objects, circles and rectangles, and it has a renderer, and that renderer handles drawing. How does renderer handle drawing? That's the question. Well, now let's take a look at that class. So if you take a look, renderer is actually just an interface. Renderer has an interface, and technically it could be an abstract class, but in this case, it is just an interface. And it defines how to draw a circle and a rectangle. These classes are defined, these methods are defined in the interface. And these take in just simple Java objects. Now, in theory, I could also pass in the object itself, but that creates a mutual dependency. That gets a bit yucky, so we want to avoid that if we can. So now, my color renderer, and technically I'm not doing actually any drawing here. You can see I'm just printing what I'm drawing a circle in color, rectangle in color. This is my color renderer class, and it would simply implement the draw function for circle in color and the draw function for rectangle in color. Similarly, we have grayscale, which should be implemented much the same way. So if we think about this, the way this bridge pattern works, let's say that I went to shape and I created a new shape. Let's say class circle, not circle, class triangle extends shape. If I add this class, and I can add the relevant methods, at some point I would need to tell Java how to draw this. So what I would do is, similar to this class, I'd have a constructor that would take in a renderer, and I would somehow take this in, and maybe I take in some other fields, maybe 6 coordinates, an x0, an x1, an x2, and a y0, a y1, a y2, whatever, something like that. For the sake of time, I'm not going to write all that, but you can imagine how I would take in that. But the point is, the draw function would also just simply be my renderer.draw, but now I need to define a new method, draw triangle. And then let's say that would take in whatever coordinates I take in through the constructor. I'm not going to write them for time, but this would also take in, say, x0, x1, x2, y0, y1, y2. Now I would need to implement this method in the interface, and then in the concrete classes, I would also need to add it. So effectively, what I'm doing is I'm avoiding creating additional classes by instead creating additional functions. So every time I add a shape class, I add a function to each of my renderers. But every time I add a renderer, I don't need to add anything to the shape class. The shape class doesn't need to change at all if a new renderer is added, because the shape class is actually only aware of the parent interface, my renderer. It doesn't need to be aware of any of the underlying classes, because the client, coming back here, the client chooses which subclass to use. And so it makes maintaining shape easier because it doesn't actually depend on any of the subclasses of renderer. And the renderer, in this case, simply has to, anytime a shape is added, add functions here. We don't need to add new classes every time we add something. We don't need to add a bunch of new classes. And this connection here specifically, this shape has a renderer. That is the thing called the bridge. And by the way, this code, of course, is uploaded. It was uploaded actually on Tuesday. So I know this is fairly nuanced, fairly abstract, but I do want you to be able to see this. The advantage is when I do my bridge demo, I can create, say, a list of shapes. I can then add a grayscale circle or a color rectangle, or I could also do shapes.add new triangle, new and then in parentheses here, new grayscale renderer. The point being, it allows me to mix and match. This allows me to mix and match the object in the inheritance. That is to say, the concrete shape, it allows me to mix and match it with the renderer where I can have any combination of this concrete realization with any combination of this feature implementer. That is to say, I can vary the shape and the renderer independently because they have separate hierarchies. So going back once again to that sentence, decouple an abstraction from its implementation so that the two can vary independently. The implementation being the square, the triangle, the circle, the abstraction being the thing that deals with drawing. Are there any questions about the bridge design pattern before we move on? This one's a bit more nuanced to see when you would use it. But again, the idea is if you need to be able to mix and match features, the bridge design pattern is a fairly efficient way to set that up, which allows for highly maintainable code, where you can add new implementations without changing the class that uses the implementations. All right. So with that, the next pattern we're going to discuss is one that if you see it, you'll think, oh, that looks cool, and then we'll just describe what it looks like. And this is called the decorator. And the decorator design pattern lets you do some cool things like, where is it? Drink demo. Like this. It lets me define a coffee with milk as new milk, new coffee. Or a double shot, new espresso, new coffee. Or maybe, because we're just really struggling to get through the day, let's call this not safe. And then, we can just do one of these numbers. Maybe that's enough caffeine to get us through the day. We need a few closing parentheses here. This almost looks like Lisp code at this point. Do I have enough parentheses? 1, 2, 3, 4, 5. There we go. Yeah, this is, by the way, if you've ever programmed in Lisp, you know that's what this looks like. This is a valid Java line of code. And you could think of this, if this is a double shot of espresso, this would kill you. I don't know how much caffeine it would be, but it would be a lot. Probably be pretty expensive too. It also can be used in a more practical sense for things like adding, say, features to a window, like horizontal scroll bars or vertical scroll bars, etc. And the idea of the decorator design pattern is actually based on a fairly simple structure. Here it is. The idea is we have some base component, which is an abstraction. We have multiple concrete implementers of this. You can actually do this, by the way, with only one concrete implementer. But the point is, you can have 2 or more concrete implementers as well. And the component is also used, and this is where it's a bit weird, because normally I say don't do 2 relationships. But this is actually relevant. The decorator both has a component, and the decorator realizes component. And the decorator in this case is actually abstract as well. So the decorator is implemented by concrete decorators. But the key is the decorator class both contains a component and extends component. And so, if we take a look at the code for drink, let me close all first. You'll see that this is our base class. This is our base abstract class, drink. And the drink has a price, and it has a toString. From there, we have a class coffee, which is just a fairly simple object. Price is $2, toString is coffee. And then we have T, and the T is $1.50, and toString is T. So this is the abstract class. This is the base component abstract class, and these are the concrete base components. So taking a look at our UML diagram, this is drink, this and this are coffee and tea. So coffee, tea, this is our drink. And this is straightforward. This is just an abstract class implemented by two concrete classes. Pretty straightforward. From there, we have our decorator class. And our decorator class we call, in this case, ingredient. And ingredient extends drink. So, notice this line here. Decorator extends drink, or excuse me, ingredient extends drink. So ingredient extends this base component. Pardon me. From there, it also has a drink component. This is a has a relationship. So the ingredient, which is the decorator class, has a base component class. So that is this relationship, the has a relationship. Now notice, because of the way this is structured, the component class is not aware the decorator class exists, and it doesn't need to be. That is a benefit. There is no mutual dependency here. The decorator depends on the component, but the component does not depend on the decorator. And we need to maintain that relationship. So from there, we have getPrice and toString, and those return baseDrink getPrice and baseDrink.toString. So all this would do is this would pass to the parent, hey, what is your price? What is your string? And it would return that. But now, let's take a look at two concrete implementations of the decorator. We have milk, and I'm going to skip cream. We'll come to that later. We have milk, and milk, when we create a milk, it calls the parent constructor with the base drink, which sets the parent variable's base drink to D. GetPrice returns the parent class's GetPrice plus 25 cents. ToString returns the parent class's ToString plus with milk. Take a look at Espresso. Espresso, same thing. GetPrice, it's the parent plus 75 cents. ToString plus Espresso. And this is the basis of what lets me do, and by the way, we're going to skip cream for now. This is the basis of what lets me do things like here. This might be, say, a latte, a coffee with milk. And if I print this line, oh, sorry, I have the wrong thing running. Run drink demo. And if I print this line, you'll say coffee with milk costs 2.25 cents. Let's look at that. Coffee toString is going to give me coffee with milk. Coffee getPrice is going to give me the price of coffee, which is $2, plus the price of milk, which is 25 cents. And so if you want, say, a latte with a shot of espresso, I can make that for you. Drink latte espresso equals new espresso, new milk, new coffee. Misspelling of milk. But otherwise, that is correct. This allows you to combine as many decorations onto a base class as you want, even if you want redundant decorations. And the key is all of these constructors simply take in a base component, and the base component is not an ingredient. That needs to be said. The base component cannot be added to a base component. I cannot say, for example, new coffee. This isn't allowed because coffee is not a decorator. It is a component. So the rule here is you can have as many decorations as you want, but you need exactly one, no more or less, base components. So, as many decorations as you want, but exactly one base component. And a practical example where you will actually see this, because this is admittedly a bit ham-fisted, is something like if we have, say, a simple window class, we have this interface window, or an abstract class window. This would be my base component. And let's say I have a simple window that just returns a simple window. From there, I have this window decorator class. The window decorator class implements window and has a window. From there, I have a draw, which delegates to the base window, hey, you know how to draw yourself, window, just draw yourself, as well as get description. But if I wanted to, say, add a vertical scroll bar, what I would do is I would override the draw method to first say super.draw. That is, draw the parent window, just as you normally would. But then add the vertical scroll bar. Similarly, I could do draw a horizontal scroll bar decorator, and this would draw the window and then draw the horizontal scroll bar on top of it. And the advantage of doing this is it's going to let me do something like, and let me go to the simple window, something like, let me do a new class real quick. Window demo. Public static void main string args. Window, my window equals new horizontal scroll bar decorator, new vertical scroll bar decorator, new window. Oops. Not what I meant to do. Sorry, not new window, but new simple window. Sorry. New simple window. And let me just space these out a bit. It seems weird that you're adding decorations around the base when intuitively it feels like you should be passing the other items in the constructor coffee. So the basis here is that this allows us to create decorations on top of some base product without the base product being aware of them. If the coffee constructor needs to take in the ingredients, that creates a dependency from the base drink to the ingredients. I'm trying to make the base drink ignorant of the ingredients, and so I'm reversing that dependency. The ingredients instead is aware of the base, but the base does not need to be aware of the ingredients. And again, this would let me do something where my window class doesn't need to be aware that scroll bars exist. That the scroll bars will take care of themselves on top of the window, but then it keeps the window class itself simple. I'm not adding any, there's no coupling. There's absolutely no coupling here. Where's their coupling? Coupling means a mutual dependency. Where is their coupling? Remember, this is a one-way dependency. So decorator certainly has a component and realizes a component. So decorator certainly depends on component, But the point is, component does not depend on decorator. The component's completely unaware the decorator exists. Where would you go to get a list of all the ingredients? So if you wanted a list of all the ingredients, you could go to the source code. You could see which classes implement this abstract class ingredient. That's how you would get a list of it. There's no controller. This, again, this would not be something that we're talking about a 3-tier architecture with. The point is all the ingredients in a particular drink. So what you would need is you could do something like this. I mean, I can show you if you want to do that. I mean, I solved that problem by adding in the toString function. If I add this toString function, all I need to do, let me go to drink demo to get the ingredients. System.out.println latte espresso. And if I do that, look, there are my ingredients right there. Coffee with milk and espresso. I simply did that with a creative use of super. But if you want to iterate over each shot of milk in the coffee, I mean, again, and I feel like I'm not trying to be obtuse here, but I mean, you could do something with a loop here, just using class hierarchy. You could say something like, object O equals latte espresso. And then something like, while O instance of drink. Actually, no, that won't work. I mean, I could just do something like system.out.println o.getClass.toString, or in this case, .getName. And that's going to give me structural decorator espresso. That's the name of the class. But again, I don't see why you would ever do this. I want to be really clear. I've never done this, and I don't see why you need to. So, I mean, but you could do this, and then you could do, okay, o.super.getClassName, except in this case, sorry, not that. It would be latte espresso, and actually I could change this out with latte espresso and get rid of O. But yeah. Well, the whole point of abstraction is to give up control. Because if you have control, that means you have to know what's going on. Like the entire point is to remove the control from certain parts of the program. Limit how many parts of the program have awareness and therefore have control. You're trying to make it hierarchical. That's the goal. If you want to iterate through a list of something, I don't see why you would use a decorator. That's not something you need. The entire point of the decorator is you should never need to. If you need to do that, then you're doing something that you probably shouldn't do with a decorator. For example, with the simple window, I don't need to with this window example. I don't need to know that this implements both horizontal and vertical to use the window, because the window object, or excuse me, this object will take care of all the features, because those features are implemented in the decorator. So the entire point is to remove the dependency of the base component to its decorations. And again, it lets you build objects customizably at runtime that combine different decorations on different base components. So it's another kind of mix and match tool that would be similar to what you could do with a bridge, but the difference here is where a bridge generally is connect one implementation to one feature. It is, in this case, add extra features on top of something that is already itself a functioning thing. All right. So again, baseline component here. This is all addressed in the slides, so I'll move on for now. I'm going to skip over observer for now. And instead, let's take a look at the adapter pattern. And one issue that everyone always has in this day and age is charging their phones. This is a USB-C. There you go, USB-C. The problem is my headset here is micro USB. And that means that I need different cables to charge these. Now what I could get is I could get a micro USB to USB-C adapter, although I would actually lose the advantage of USB-C if I did that. I could also get a USB-C to a micro USB adapter. But the idea of an adapter is to take something legacy, and legacy, and I'll write that out in software. I've mentioned this term before. Legacy means thing that already exists, that you may need to build on top of. And the idea of the adapter is to take something legacy and translate to a different interface that might be more maintainable or might adhere to new standards in the program. Let me give an example of this. And again, this is here inside of structural. The idea is I have two legacy classes. Let's say this is a line. It goes from point x1 or point x1 to point x1 y1, to x2 y2. And so, oops. Sorry, I didn't have my whiteboard camera set up. I'm knocking everything over. Give me 1 second. So I'm defining a line more or less by some kind of rectangle here. Let me turn this light off to reduce glare. So I have x1, y1, and x2, y2. And I've defined this line. Additionally, I have this legacy rectangle, and this takes in an x and a y center coordinate for a rectangle, and a width and a height. So I might have something like this. That is my width. That is my height. And this point there is x1, y1. Now, right out of the gate, these two interfaces are quite different. I'm defining effectively two endpoints for my line, whereas I'm defining a center and a space around it for a rectangle. And so, one issue is these classes, as they're written, are not related. Notice there's no shared interface here. And so I could create a list of objects, legacy line, legacy rectangle. I could then, if I wanted to, let's say, treat these as the same. And here, let me explain what I'm trying to do here, actually. What I'm trying to do is I'm trying to redefine how I draw a rectangle to be similar to a line. The way I'm going to draw a rectangle is I'm going to define the two corners, and then I'm simply going to connect them with right angles to form a rectangle. So I want to make the rectangle adhere to this interface. And this can be done with simple mathematics. If this is called x and y, then this point is x minus width over 2, y, and this is up, so plus width over 2, or plus height over 2. And then this point down here would be x plus width over 2, y minus h over 2, etc. I could draw the rectangle this way, but if I want to do that, then it takes quite a bit of work. So first I have to say, okay, if the object, because remember this is an object array, because that's the only shared parent class they have. If this object array has a line and a rectangle, and they're both defined in this way, that is with these dimensions, then I have to do first, if the legacy line, or if the class is legacy line, I'm simply going to draw that line shape, call the draw function from x1, y1, x2, y2. But if I'm trying to build a rectangle with these same points, I'd have to do a lot of work here. It's kind of a pain. If I want to draw a rectangle from top left corner 1020, bottom right corner 3060, or technically this would be bottom left and that would be top right, whatever. In order to adhere to this legacy rectangle, I have to do a lot of math here. And I don't really want to do that. So how can I avoid this? What I'm going to do is I'm going to define a shared interface that both the rectangle and the line will adhere to, that whenever I provide 2 points, let's say this point here and this point here, if I want to draw a line, I use those 2 points to draw a line, and if I want to draw a rectangle, I use those 2 points to draw a rectangle. So I'm matching up these interfaces. So you can think of this, again, the idea is I want the same interface to apply to both of these classes, the same way that I want the same charge cable to work for my headset and my phone. So in order to do that, I'm going to define this adapter situation. And the adapter, or the better adapter, I should say, is this adapter is going to have both of these classes implementing some interface called shape. And that interface is going to involve a single draw function, x1, y1, x2, y2. And this interface will work on both a rectangle and on a line. From there, the line class is going to have a legacy line. It's going to have something that it's adapting, an adaptee, that is the thing being adapted. And then if the draw function is called with x1, y1, x2, y2, well, we don't really need to change what happened. So we can simply say, call the draw function as it is. From there, in the rectangle, it's going to have its own legacy rectangle object, the same way that the line had a legacy line. But the way we implement draw is we call the draw function with the correct arguments. But here's where that's advantageous, because now the client just simply creates a list of shapes. They define their points. They create their objects with the new line, new rectangle. And they can simply use x1, y1 on both of these. This is easier for the client. Because remember, the client, the person using the adapter, will only need to see this. So yes, the code that does that adaptation, the math is still there. But because we added an adapter, the client never needs to use that manually. And further, this will be very dry. That is to say, you won't need to repeat yourself because you can just use the adapter. And the advantage is you're still actually using that legacy class. So any other features that the legacy has, you still have access to. You've only added an adapter. You haven't completely reprogrammed everything. And so the class diagram for this would look a bit like this. The idea is we have some client working with an adapter. The adapter is using some adaptee. The client just calls adapter method A, and the adapter calls the associated method with the correct modification of arguments for method B. Do I have the... I don't have... I used to have a good example for this, which was to make a square peg fit into a round hole. But I don't have that. I'll see if I can dig that up and pull it back up. That's the idea of the adapter. That is, take some legacy part of the program and add a new interface onto it to make it correlate better with other interfaces in the program. Another similar example to this is a facade. And a facade is, and this, I don't really have any code examples for this, but the idea of the facade is that we take all of the systems and we create a single point of entry for all of these systems that's designed to make this simpler to use. That is to say, the user only interacts, in this case, with subsystem 2 wrapper, but it, by only interacting with this, they will use all of these different features all at one point. The last one I'm going to talk about is the observer. And the observer is the basis that we will want sometimes objects, whenever they change, we will want to notify the rest of the program, hey, this object has changed. So, for example, let me find my, here we go. So, for example, we have some object, I'm going to call it subject, and subject is owned by some other class, observer. And the idea is subject at some point is going to have some function called on it by, say, the client. And the client may call this function on subject, and this will necessitate changing some field. What I want to do is every time this field changes, maybe the observer needs to do something. Let's say I change some state variable. Maybe that necessitates that I update or call some function in observer. Thus, in order to do that, what I'm going to do is define an interface. Now, what I don't want is I don't want subject directly calling a function in observer. Because now we have a mutual dependency. That's bad. Rather, I want subject to have a generic idea that it is being observed. That is, you think of subject as paranoid. It's being watched. It knows it's being watched. But the key is, it doesn't know by who. It doesn't know who's watching it. Because we don't want subject to depend on anything watching it. We just want it to know that it's being watched, so that it will notify every time something relevant changes. So how can we do this? Well, the basis here is the idea of an object and observer interface. And by the way, this code was uploaded, though it's not in the observer folder in the upload from Tuesday, so I just re-uploaded it separately. We have this interface subject, and the subject is going to contain a list of observers. And the subject is going to have a function called attach, and this is where it attaches an observer to its list. It also has a detach, stop watching me. But then it has a function notify all observers. And it's simply going to loop through the list of observers and say, hey, something has changed, come check it out. Similarly, we have this observer class, and this observer class just defines a function update. Now here's the advantage of this. What actually is happening here, and I'm going to modify my whiteboard now, is I'm going to change this to say concrete subject and concrete observer. These are realizing subject, the abstract class, and observer. And the observer does have it lists, or the subject, lists observers. And the observer is realized by the concrete observer. Now you may be thinking, wait, is there a cyclic dependency here? There isn't. Here's the key. While the concrete subject is aware it's a subject, it will simply call notify all, which will inevitably use this list of observers. So I guess you could argue there's some dependency here. But the key is this. The concrete subject has no clue why the observers are observing. It simply provides some level of saying, hey, something has happened. You can be aware something has happened, and it notifies it. And the advantage is this is actually often used in multi-threading, although in today's class I'm not going to get into threading because we haven't really talked about it in this course until now. And so, let's take a look at a specific example. Here I have an integer subject that extends subject. And it has a constructor that takes in some integer. It has don't have screen share on. Here I have a class integer subject that extends subject. And that has an int state. So this is a pretty standard. It has a getter and a setter. But the key with the setter is every time that state variable changes, I want to notify all observers. Now notice at this point, I haven't said anything inside of integer subject. Nothing in here says how it's being observed, says what will happen when notify all observers is called. It simply is aware that it is being watched because it extends subject, and in doing so knows to occasionally call, whenever something changes, notify all observers. The observers then are notified and they perform some kind of update. And whatever that update is, that's up to them. The observer specifically is going to be aware that it is observing some integer subject. It's going to be aware that and this is has a relationship. It's going to has a subject. Specifically, this extends technically integer observer, and the subject is defined up here. But technically, all these observers do not have to share the same inheritance structure. We could have as many observers as we want that have nothing to do with each other. But the key is they have a subject. They have an instance of subject that they're attached to at creation time. So here's my Hectl observer, takes in this subject, this dot subject equals subject. It then attaches itself to the subject. So notice I never say inside of my integer subject class, I never call attach. Because if I called attach, if I said, hey, attach this observer to you, well, now the class has to know what that observer is. And we want to limit that understanding. So instead, and while this may seem a bit weird, the observer attaches itself to its own subject here. And then every time it's updated, we're simply going to get the state of that integer. And in the case of Hectl, we're going to create a 2-hex string. In the case of binary, we're going to create a binary string. In the case of octal, we're going to create an octal string. Now let's see what that looks like from the client side. The client creates some subject. The client then creates a Hectl observer that takes in that subject, an octal observer that takes in that subject, and a binary observer that takes in that subject. I'm then going to update the state to 15, and remember that set state inside of integer subject calls notify all observers. It doesn't know why it's calling it. It just knows, hey, I'm being observed. So let me update everyone that, hey, something's changed. Might want to check and see if you need to do anything. Then we call set state 10. This is going to update the state again. Let's go ahead and run this and see what it looks like. And what you'll notice is that after I do my first state change 15, the hex string, binary string, and octal string all print. Even though the subject is not aware it's invoking that, notice the subject again. It's not even aware how many things are watching it, what object data type is watching it, whatever. It doesn't have to be aware. It simply says, by notifying all observers, that will go to this subject class, and everything that's observing it will be updated. And then each observer is responsible for their own update method. So the hex, for example, says hex string get straight, .2 uppercase. The binary does a binary string on that subject get state, and the octal does subject get state octal string. And so, the subject doesn't need to be aware of what's observing it and for what reason. It only needs to be aware that it's being observed by something. It doesn't even need to know the class type that's observing it. It just needs to be aware that something is observing it. And that will automatically trigger what the update methods print. So for example, it prints hex, octal, binary, hex, octal, binary. So again, here's the basic idea. The subject, technically this arrow's backwards. This is an old diagram I found. But the observer has a subject. Sorry, the concrete subject, I should say first, is a realization of subject. So a lot of the arrows are backwards. I'll replace this diagram and re-upload. Let me just go to the whiteboard because that's the better diagram. The subject is extended, that is realized, by the concrete subject. The observer is extended by the concrete observer. The concrete observer has a subject, and the subject class has a list of observers. So that slide is actually not particularly helpful. I will probably just delete it and then just re-upload a picture of the whiteboard there. From there, again, you can think of the call graph. This is another UML diagram that we didn't go over, but this is a call sequence. The idea is, at some point ahead of this function call where we start, the observer and observer 1 and observer 2 attach themselves to subject. That is, they subscribe to it. From there, subject does something that triggers a notify call that updates observer 1, which performs some action, and then updates observer 2, which performs some action. And again, the advantage, the subject is completely unaware of what that is. Another example of this, you could use it, let's say you need to log to multiple sources. So the subject uses some type of logging. It has a logger and it says, okay, I need to be able to do some type of logging, so I'm going to log an event. That log event triggers notify. That notifies all of the loggers that are observing. Say screen logger, which logs to the console, database logger, which logs to a database, and file logger, which logs to a file. So it logs to all three sources when relevant. The point is the subject is aware it's being observed. The subject has a way to attach and remove observers, but the observers actually call the attach and remove. And then the logger is just an interface that tells all of the implementers, hey, you need to update. So that's the basis. Are there any questions? If there are no questions, that's design patterns. Those are the ones we've covered. So just to reiterate the design patterns that we covered, and I will upload readings for the design patterns I just discussed. But to discuss the design patterns, day 1, we talked about singleton, factory method, and we talked about, what was the last one? On the homework, I'm actually just mentally blanking here. Strategy. That was it. We also talked about anti-patterns, but those aren't really design patterns. Day 2, we talked about bridge, decorator, adapter, and observer. And we also mentioned facade, although we don't really need to get into example because it's a fairly self-explanatory idea. It's just putting up a simpler class on top of an interface of more complicated classes. One or more complicated class, I should say. These are the only design patterns I will expect you to know for the exam. These 8. And I will upload some reading for all of them. Although, again, facade and adapter are similar. The idea of an adapter is to take a class and make it adhere to a modern interface or an interface that another interface you're trying to make it adhere to, something legacy, port to the future, effectively. The idea of facade, take something complicated, make it simple. Any questions about any of these design patterns? How much coffee will kill you, calculator? Oh, sorry, yeah, it does censor links. Just put a space after the period. Oh, was that it probably was a web link. Yeah. I just have to block it because early on, there were a lot of people on Twitch trolling classes. And, let's just say there were multiple times, even during this class, which is smaller and got less attention, that the auto mod has kicked in for someone joining the chat and dropping obscene emotes. And by emotes, I mean ASCII art. So, yeah, unfortunately, I just have to do that. All right. So with that, I will fix the one slide with the bad diagram. Admittedly, that's a diagram that I just quickly pulled off the web and thought, oh, that's probably right. And it's not. It's completely wrong, in fact. Like, all the arrows are backwards, so I'll fix it. But, yeah, that's all I have for now. Are there any questions? If there aren't, that is the last day for new material. I remember a while back when there was a random viewers like, yo, what's up, Twitch? Yeah, no, so that's one thing is I did have more random passers-by, but that's because I was streaming, like I had the category set to IRL and educational, and so people would find them by browsing those categories, but there were enough people trolling by also browsing those categories that I just removed them because it made it less likely that my class would get interrupted. You know, just it's one of those, I've never done this before this term, and so we kind of had to learn by doing. Well, then I love you lots. Only drink 83, maybe 82 to be safe. By the way, what's the time frame for this? Because, like, you know, certainly if you drank 83 cups of coffee over a year, you'd be fine. Is this like in a day? Because I don't even know if I physically could drink that much coffee. I think I would like have significant problems. Like you would drown if you tried to drink that much in a day. I think it's daily. How many days in a row do you have to drink 83.7 cups of coffee? This is very ambiguous, this measure you're sharing. Sorry, I'm being trolling. All right, well, that's the last day of class for new material. So we will have the exam review on next Tuesday. That will be the last day of class. And that'll be it other than the exam. My goal, again, is to try to have homework 5 and 6 graded before the 28th deadline where you have to set credit or no credit, as well as all the quizzes graded. I know I haven't graded Quiz 7 yet, so I'll try to get on that this weekend. But we'll do the best we can to get everything up. And that will be it. So I'll see everyone Tuesday. Have a great weekend. Take care.